Hey everybody, today we are going to talk about operations with vectors. We are going to find the magnitude and direction of a vector, multiply a vector by a scalar, and add and subtract vectors specifically. So let's look at this very first example right here. It says, suppose the base of a robotic arm is secured at 0, 0, and its movement is limited to the XY plane. A drawing of the arm is shown below. So the base of the robotic arm is 0, 0, and then this is the robotic arm right here, okay? You guys can kind of picture that and see that. Number 1 says, in the coordinate plane next to the diagram, draw two vectors to represent the 10-inch and 13-inch parts of the robotic arm and label them as vector u and vector v, respectively. So, vector u, we're going to say, is this 10-inch part of the arm. So it's going to go start at 0, 0. It's going to go 6, 8. These are very small. Okay. Here's vector u. All right, and then the 13-inch arm is vector v. So it starts at 6, 8, and it ends at 18, 3. So there's 6, 8, 15, 16, 17, 16, 17, 18, 1, 2, 3. So we're going from here to there. And that is vector v. Check. All right. It says write the vectors u and v in component form. Vector u is the horizontal distance is 6 and the vertical distance is 8. And the component form of vector v, the horizontal distance was, let's see, we start at 6 and go to 18, so 18 minus 6 is 12. And then the horizontal distance, we went from 3, or wait, we ended at 3, I'm sorry, and started at 8. So that vertical distance was minus 5. So we went down 5, so we went right 12 down 5, okay? Alrighty. You can also find that by thinking of doing the head minus the tail. Okay, and if you can't remember which part's the head and which one's the tail, remember this is considered the head and this is considered the tail. Okay. Alrighty. So check number 2. Number 3, draw a vector from the base of the arm to the end of the arm. What does this vector represent? So draw a vector from the base of the arm to the end of it. What does this vector represent? Well, the position of the end of the arm relative to the base. So this is the base and this is the position of the arm. So it is the position of the end of the arm relative to the base of the arm. What is its component form? So that component form, this coordinate point was 18, 3, so it'd actually be 18, 3. Okay? And again, you can do the head minus the tail to find that component form. The third vector you draw represents the sum of u and v, or vector u plus vector v. Describe the relationship among the component forms of these three vectors. So the sum of the component form of vector u plus vector v is going to be equal to the horizontal component of vector u plus vector v, and same for the vertical component. So basically all I have to do is add the horizontal distances together, the horizontal components. So 6 plus 12 is 18, and then I add the vertical components. 8 plus negative 5 is 3. Okay? All right, you saw above that you can add two vectors, vector u and vector v, geometrically by drawing vector v with its tail at the head of vector u. The sum of the two vectors is then the vector form of the tail of u and the head of v. You can also add two vectors geometrically by using properties of parallelograms as shown in the next example. I am actually not going to do the parallelograms. I'm going to go more this route by drawing v with its tail at the head of u. So I'm going to draw vector u, and then from vector u we're going to draw vector v. So just want to add over here, the sum of two vectors is known as the resultant vector. So when you add the two vectors together, that's called your resultant vector. It's just a little vocab. Alrighty, so example A says add the vectors u equals, vector u, component form is 2, 4, and vector v is 5, negative 2, both geometrically and symbolically. So like I said, we are not going to do this like parallelogram thing over here, but you're going to draw vector u, so whichever one comes first, okay, in standard position, so 2, 4, and then we are going to from u draw vector v. Okay, so vector v was 5, negative 2. So from here, 1, 2, 3, 4, 5, and then we're going to go down 2 because it was minus 2. And look, that takes us to where that resultant vector is of the two added together. All right, so don't worry so much about the parallelogram. All right, think about going from this head and then to draw vector v. Okay, because no matter what, as long as, because we're in component form, as long as your horizontal distance is the same as the component form and the vertical distance is the same as the component form, you can move this vector anywhere. Okay, so that's why we don't need to draw it down here and then do the parallelogram. Symbolically, when you add the vectors, or the horizontal components and the vertical components of the vectors, so you would do 2 plus 5 gives you 7, and 4 plus negative 2, which is written right there, gives you 2. Okay, so let's do these. So let's try these A. Add each pair of vectors both geometrically and symbolically. So I'm going to do these over here off to the side. So we've got S, which is 4, 1, 2, 3, 4, 1. So that's vector S. And then vector T, so I'm going to start from the head of vector S and go left 3, 1, 2, 3, and up 4. 1, 2, 3, 4. And this is vector T. And that ends at the coordinate point of 1, 1, 2, 3, 4, 5. Okay. Sorry guys, I kind of had that off the page. Apologize. So this would be 1, 5. So that's geometrically. Symbolically, this would look like 4 plus negative 3, comma 1 plus 4. So 4 plus negative 3 is 1. 1 plus 4 is 5. Okay? All right, let's do example B. So we've got negative 6, negative 5. I might go, trying to think about where this might be. Okay, so negative 6, 1, whoops, 1, 2, 3, 4, 5, 6, negative 6, 1, 2, 3, 4, 5. That is vector Q. Guess I could have counted by 2's. And then from this head, this is going to be the tail of R. So 1, 2, 3, 4, 5, 6, 7, 8, and down 5. 1, 2, 3, 4, 5. Oops, let's roll that down further. So this is vector R. Okay, so that coordinate point is 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 2, negative 10. So that component form would be 2, negative 10. All right, and then let's check it symbolically. So we would do negative 6 plus 8, comma, negative 5 plus negative 5. Yeah. Sorry, I thought those were going to cancel. So negative 6 plus 8 is 2, negative 5 plus negative 5. That's negative 5 minus 5, basically, which gives you the negative 10. Okay? Alrighty. We're not going to do the check your understandings. I'm going to skip that part for right now. Okay. So down here it says the additive inverse of a vector W, denoted as negative vector W, has the same magnitude as W, but points in the opposite direction. So this additive inverse has the same magnitude as W, but points in the opposite direction. You can subtract one vector by another by adding its additive inverse. In other words, if you have vector U minus vector W, that is equivalent, or I'm sorry, that's vector V, my bad. Vector V minus vector W, that's equivalent to vector W or V plus the additive inverse of vector W. Okay, so when we mean that the W is going to point in the opposite direction, that just means change the signs of the vertical and the horizontal component. Okay, so it says use the vectors V and W for items 8 through 11. So what is the additive inverse of vector W? So this is the notation we're going to use here. And like I said, you're just going to change the signs. So this negative 2 becomes positive 2, and that 5 becomes negative 5. The magnitude is not changing. The only thing that's changing is it's pointing opposite direction. Originally it was going left and up. Now we're going to the right and down. Okay. This math tip over here says two vectors are additive inverses if their horizontal components and their vertical components are opposites, which is basically what I just said over there. Okay. I am actually going to rewrite these two vectors up above. So I can refer back to them. Oh, sorry guys. I just wanted to write them up top so I didn't have to keep flipping. Alrighty, so it says use the coordinate grid to show how to find a vector V plus the additive inverse of vector W geometrically. So we have 3, 1, 2, 3, 1, 2, 3, 4. So there's vector V. And then we're going to do the additive inverse of vector W, so that was 2, negative 5. So we're going to go to the right 2 and down 5. 1, 2, 3, 4, 5. Oh, whoops. A little off, sorry. 1, 2, 3, 4, 5. Okay, and so that was at the coordinate point 5, negative 1. So it says, what is the component form of vector V minus vector W? So vector V minus vector W is 5, negative 1, and we just found that right here. Explain the answer. This is actually equal to the same thing as V plus the it's equivalent to the additive inverse of W, which is also 5, negative 1. You guys can see if I do 3 minus negative 2, that becomes a 5. 4 minus 5 is negative 1. So that's kind of a way to look at that as well. If you want to put, that was the additive inverse. Okay, number 11. What is the relationship among the component forms of vector v, vector w, and vector, oh, we're not doing this actually, sorry. I meant to skip over that one. All right, number 12. Given that vector s is negative 2, 2, and vector t is 1, negative 4, subtract each pair of vectors both geometrically and symbolically. So we're just doing some more practice right here. So let's see, vector s is negative 2, 2. So it's vector s. And because we're subtracting vector t, this is really going to be I don't know why I put that in parentheses. You don't need to. It's the vector s plus the additive inverse of vector t. So this would be negative 1, 4. So left 1, 1, 2, 3, 4. And that happens at negative 3, 6. And if we want to do it symbolically, that would be negative 2 minus 1. You can think of it like that if we're focusing on these guys right here. And then we would do 2 minus, because we're subtracting, negative 4, which gives us negative 3. This becomes positive 4, so 2 plus 4 is 6. So a couple different ways to look about that. Okay. Oh, this is additive inverse of t. All right, letter B, we're going to start with t. So vector t was 1, negative 4. And then we're going to subtract vector s, or you can do the additive inverse of vector s. So that guy would be 2, negative 2. So we're going to go right 2, down 2. Leads us to there, which is at 3, negative 6. Okay, and then we will do symbolically, we would start with t, so 1, and you could do minus s, so that's a negative 2. And then we would do negative 4 minus 2. So we get 3, and that equals negative 6. Okay, so a couple different ways to look at these. Notice that the order does matter, so just be careful that you're always drawing the first vector in standard position. Okay, the one that's listed first. All right, a scalar is a quantity that can be represented by a single real number. You can multiply a vector, vector u equals ab, by a scalar h as shown in the next example. So it says multiply vector u equals 2, 1 by the scalar 3, both geometrically and symbolically. So that looks like this right here. Okay, so this is basically saying take vector u and add it to itself 3 times. All right, so thinking of the from the head to the tail method idea, or end to end. So you draw vector u and then draw vector u again, and a 3rd time because there's a 3 out in front. Okay, so kind of think of that end-to-end method that we were doing before. Okay, so it says draw 3u with the same magnitude and direction as vector u plus vector u plus vector u, and that's what was shown on that last page, and that all equals this one big long vector, which is 6, 3. Symbolically, you can multiply each component of the scalar. So vector u was 2, 1, I believe. Let me double check. Yep, it was 2, 1. Okay, So we are doing 3 times the horizontal component and 3 times the vertical component to get 6, 3. So that's the symbolic way. All right, let's do these real quick on the try these be. I'm going to do them off to the side over here. Let me actually move my paper this time. So we are going to find each vector geometrically and symbolically. We're going to start with 2 times vector v. So we're at -2, 4. I have a feeling this is going to be a big one. So -2, 1, 2, 3, 4. So that's vector v. And then it happens again. So -2, 1, 2, 3, 4. Or that you could say that is the same thing as that guy. These all together. So what's that coordinate point? That was 1, 2, 3, -4. 6, 7, 8. -4, 8. Okay. Symbolically, you would just do, let's see, vector b. So you would do 2 times -2, and then 2 times 4. That's the vertical component. So we get -4, 8, which is what we have up there. Okay. I'm not going to do example B just because it's like the same idea. Now you're just doing it with W. All right. Let's do example C though. So example C, you're doing -2 W. You guys can think of this kind of as like 2 and then the inverse, or I'm sorry, the additive, the additive inverse of W, okay, if you would like. So you could, if you wanted, we know that if that is W, the additive inverse of W would be 3, 1. We're just changing the signs on the horizontal and vertical component. So I can go 1, 2, 3, up 1. That would be the additive inverse of W. And I would do it again because it happens twice. So 1, 2, 3, up 1. And altogether, that would be the -2 vector W, all of that together. So that is 1, 2, 3, 4, 5, 6, up 2. So 6, 2. Okay, if you want to talk about symbolically, you could do 2 times W, which is 3, or the additive inverse of W, my apologies. And then the vertical component was 1, which gives you 6, 2. Okay. If you did it this way, you also could think of this as -2 times W, which was -6, or -3, sorry. And then you could do -2 times -1, which you guys can see that still gives you the same answer, so 6 and +2. So a couple different ways to look about it. Yeah, that's it. We're not going to do these check your understandings either. All right, so your homework is this page right here, page 449, problems 15 through 20. Let me know if you guys have any questions.